Today we will continue with software architecture view modeling. Last time we have discussed the 4+1 view models, started from Philip Kruchten, and we have seen that this has been adopted to in UML also, where they have also 4+1 views. We have discussed the key motivation for the applying different views in architectural modeling. Today we will look at a more recent approach on architectural view modeling, which is called the views and beyond approach. I will first discuss that, organizing architectural views. We will discuss how you can choose views, how you can document behavior, and what does it mean to document a software architecture using architectural views. This was the summary last time, also a part of the IEEE recommended standard for architectural description. A key issue here is that every architectural description is organized by a set of views. Okay, a view conforms to some viewpoint, and the key motivation for applying different views was, of course, that we have different stakeholders who have different interest in the system. Okay, so it's, as a key principle, we said we should separate these concerns and model the architecture accordingly. So typically for different kind of concerns, different views. The way how to represent views is done using viewpoints, so which describes the template or pattern, and the view is actual instance of that template, representing a view of the system for a particular stakeholder who has some interest, who has some concern in the system. This was the 4+1 view model from UML. Also, we said was also from Kruchten. There they separate between 4 views: design view, process view, deployment view, implementation view, and in the middle the use case view. As we have seen, this was before called scenario view in the Kruchten's work, but this is now adopted in UML. The same motivation to depict a different view of the system to different stakeholders. Okay, so it's not easy to map all these concerns in one view. So we separation of concerns. Actually, there are different approaches have been introduced for architectural view modeling. Okay, for example, Siemens view from the excuse me, for enterprise modeling, different views modeling from the C4ISR system, different standard for views. So there are many different view approaches are available, and as an architect, we have to decide a particular view, a particular approach. So, typically, we can organize the views into some broad categories, which has been done also kind of in this book about documenting software architecture from Paul Clements et al., where they provide also a particular approach to describe views of the architecture. It goes beyond the 4 view modeling. It is broader, more general, and at some points it's also more specific. We will see how. Basically, they structure views by asking these 3 questions. How is the system structured as a set of implementation units? Okay. Second question, how is it structured as a set of runtime elements that have runtime behavior and interactions? This is more design view. or runtime view, how does it relate to non-software structures in its environment? So in the end, we have to map the software to some environment. That's the third question. Based on that, they define three view types, not viewpoint. We will see the difference later on. For the first question, how is it structured as a set of implementation units? All the views that somehow provide an answer to this question are called module views, belong to the module view category. This type is called component connector view, and the third one is allocation view. Typically represent how to allocate the elements in the module and component connector view to non-software elements. What's a view type? View type is just like a viewpoint as in the IEEE standard. It's a template to describe some views. For example, the module view type, which is our first view type, documents. The key goal is document the system's principal units of implementation. So you look at the implementation perspective, from the implementation perspective. What are the elements here? So we said architecture design. Architecture consists of set of components and set of connectors. Okay, this is a plain definition. So in that sense, we said every viewpoint, in this case view type, this has its own set of elements and relations. In the module view type, the elements represent modules. Okay. A module is an implementation unit of software that provides some coherent unit of functionality. Okay. Could be a subroutine, could be a class, a layer, etc. Okay. Some units of implementation. Here we see the legend, the key. Typically in the module view type is represented like this. Okay. So this is a class. Okay. You can use a package, subsystem, etc. The relations are, there are three types of relations here. Is part of, depends on, and is a. These are just the relation that we know actually from UML. Is part of, and some class or actually module can depend on some another module, and generalization or is a relation. Okay. This is the view type, the overall view type. You can use this view type in principle to describe views, but in the views and beyond approach, they don't take a second step, but they don't have two steps like we have seen in the IEEE standard, viewpoint view, but they have another concept which is called style. Okay. So here you have the view type, style, and then view. What is an architectural style? It's also a template from which you can derive views, but it's a specialization of view type. It provides just additional constraints on what to select from the view type. So you have the module view type, like here, this is the overall view type. Then a style says, so pick, so an element could be a class, relation could be just a part of. Okay? So it puts additional constraints on the view type, on how the element types are restricted, how they need to be combined, etc. So view type can have different type of styles. There are 4 predefined styles of the module view type. The decomposition style, generalization style, user style, layered style. It's very simple actually. Decomposition style is derived from view type. what is the relation here? What is the element? The module. So it belongs to module view type. The module is as defined by view type, which means you can just take the whole set. You can use these. But there's a strict constraint on the decomposition, on the relation, which says you can only use the decomposition relation. So in essence, it means a decomposition style is thus, you can define like this. So you can take the modules here plus a relation here. Generalization style is similar. It says you can just take the modules in the module view type, but just use the is-a relation. So if you describe architecture like that, then it's called generalization. It's an architecture view from the generalization style. Third one, user style. Module is again as defined by view type, but it specializes the depends on relation. It takes this relation, says you just should use this relation, but it also puts additional constraints on that relation. We will see how. Finally, layered style. The modules are layers. It specialized depends on relation to allow to use. So, okay, it puts additional constraints again on depends on relation, similar to user style, but it's a further restriction. It's allowed to use relation. We will see how. Okay. Well, in essence, code in higher layers are only allowed to use code in lower layers. It's a very general sense. A few, decomposition style. Decomposition style is you just take a module here. The modules are just as defined by the module view type. Decomposition style, you take this relation. I will show examples. The module view type in this view type is the complete set. If you take a style, you put some constraints. You specialize the view type. So it's not like in the IEEE standard where we have view point, view. But here we have view type, style, view. So question then, then we have like this. The view is a style that is bound to a particular system. This represents a view for some specific particular application domain. Okay. Okay. A decomposition view of an insurance system. That's here. Okay. But these are just templates, the style and the view types. So how would you relate? Is a style a viewpoint or not? If you would relate these terms. Viewpoint is a template. Template to describe some views, right? And here, what are here the templates? The grammar, okay, the language to describe some views. This is just instance, right? What are the templates here? Style is also a viewpoint, kind of viewpoint, right? You can say this is a kind of viewpoint and this is a constraint viewpoint. Okay. But here in the terminology of views and beyond approach, you have the view type, style. Okay. It's clear? If you look at the module view type, we have 4 predefined styles: decomposition style, generalization style, user style, and layered style. these represent the templates, the notations that we can use, the grammar, so to speak. And we can define the composition view by using the style, using these styles, decomposition style. By instantiating user style, we have the user's view. So we instantiate for a particular application. Example. So, well, let's look at the decomposition styles. We said the composition style, the module is as defined by the module view type. What's a module? A unit of implementation. Class, package, layer. The relation, say here in the decomposition style, the constraint is you can only use decomposition relation. Specialization of is part of. There are some topology constraints. No loops are allowed in this decomposition view. A module cannot be part of more than one module in a view. This is an example of a decomposition view. Okay? For a particular system, A7 system. This shows, for example, the system consists of 3 modules. Hardware hiding module, behavior hiding module, decision module. Okay? So view type, we'll select the decomposition style, and using the decomposition style we have our A7 system. So it's not important what kind of system it is here, but we start defining a decomposition view. Our constraint is we can only use part of, and we can show like this. A7 system. And this means this, so if it's in the system, it means it's a part of. Okay? It's first view of the system. Typically, this kind of view is shown to newcomers, new colleagues. Look, this is our system. We are working on A7 system. It consists of 3 modules. Hardware hiding, behavior hiding module, and decision module. Okay? So how did we deconstruct this? So composition from the module view type, decomposition style. And this is the system. Equally, we could also represent as a textual way. Okay? This is an example of the textbook. So we have hardware hiding module, behavior hiding module, software decision module. And here we see that hardware hiding module has 2 submodules, extending computer module, device interface module. And all these modules have their sub-modules. In a similar sense, we could use UML aggregate relation, but that would be quite complicated for this. Okay? So when do we use this decomposition style? Actually, almost all architectures begin with module decomposition. The idea is divide and conquer. Our system consists of these 3 components. Okay, that supports understandability. Okay, no need to go into details the first time. No association relation, no generalization, no calls, no allocation relations, just decomposition. Very simple. It's a means to communicate the broad picture. Also begins to address modifiability. That is the ease of changing the system. That will be built into the architecture by allocating functionality to specific places in the architecture. Okay, because you have a broad view, you decompose your system into modules. You can say, okay, you can know what you can change in your system. It's a first start to address modifiability. Different purpose for decomposition you could have. So you could decompose your system in different ways. That's another discussion actually. So decomposing based on specific kind of criteria. Here we have just seen one example. Okay, but you could have also different decomposition. The view itself doesn't say provide the criteria to do it, but that's your design decision. It doesn't say decompose like that and that. No, it just provides you the means, the tools to describe the architecture. But the decomposition should be done by yourself. Typically, you could have different criteria for that. For example, for modifiability, for performance, build versus buy decisions. If you have already some existing module, then typically that will be a separate module in your system. Okay, you will not remodularize. And for product line implementations, where you can distinguish between common modules and variable modules. So that was the decomposition style. It's clear? I'll give summary. Excuse me. What is a view type? I'm sorry.
It's how we see the under the architecture. How can I say? It's a type of applying some concepts like decomposing and
one sentence. What's a view type? One sentence. An architectural view type is a one sentence. We can provide one sentence. It's a template to describe views. Right. Where is? Yes, one sentence, a few words. What's a style? One sentence or 2 words. It's also a template, but what's key there? You constrain, okay? You constrain the view type. That's it. A constraint view type. If you say in 2 words, constraint view type. A view type, template to describe views, and from which you also describe derived styles. What's a view? It's a perspective on the system from a particular stakeholder's perspective. Okay, that's the issue. So the user style is again derived from module view type. What does it mean derived? So it considers the modules and the relations, but it puts additional constraints. For the module, no constraints. Module is as defined in the module view type. Relations, again, there's a constraint. In decomposition style, the constraint was just use the decomposition relation. Here, use the user's relation. In the module view type, we have seen there were 3 relations. Decomposition depends on and is a. The user's relation is a refined form of depends on relation. The relation is defined as here, module A uses module B, if A depends on the presence of a correctly functioning B. Example, user interface, users database. Okay. There are no topological constraints. Okay. Quite easy. User's style. This is the template, of course, and typically we could see as a part of the user's view, right? Like we had the viewpoint, view. Here we have the view type. We constrain, we get the style, we get the view. Okay. So we could have, like this is an example. In this way, this is another example of this. It's more refined. We have module A, module B, module C, which use the database. Module B uses the database, module A uses database. It's a user's style. A user's view based on the user's style. The user style is from the module view type. What's the key issue here? Representing the architecture based on the implementation units. So these are all implementation units. Users relation can also be documented as a two-column table with using elements on the left and the elements that they use on the right. So this element uses these elements. Okay, like we could represent the decomposition view also textually. We can do this also for the user's view. Okay. The user's relation is not the calls relation. That's a confusion. This user's relation is a special form of depends on relation. We say P1 is set to use P2 if P1's correctness depends on a correct implementation of P2 being present. That is, P1 depends on the result of P2. If that's not the case, it's not a user's relation. A user's relation is not calls relation. For example, a program P1 can use P2 without calling it. Okay. For example, how can this happen? For example, the P2, this should be 2, leaves updates a shared variable that is used by P1. Okay. P1 doesn't call P2 directly, but somehow P2 accesses some shared variable which is accessed later on by P1. Okay. In a similar sense, program P1 can call program P2 without using it. P1 calls P2 but doesn't use. What does it mean? The P1 does not depend on the result of P2. For example, P2 could be an exception handler. It just says an error occurred. P1 doesn't care what P2 does. Okay? It doesn't use. It's a somehow detailed discussion, but important one. And we come to the third style, the generalization style. Here the module is as defined in the module view type. Again, the relations is the generalization relation, is a relation of the module view type. You select just one relation. Topology, constraints, cycles are not allowed. That is, a child module cannot be a generalization of one or more of its parent modules in a view. A module can have multiple parents, then we have multiple inheritance, but this is usually not preferred. What is a generalization view? This is an example of generalization view. Imagine we are building radar systems. Then we could typically define in the views and beyond approach, define a generalization view by using the generalization style. Then we get this as an example. These are the modules, in this case classes, and this inheritance relation. You are not allowed here to put users relation, decomposition relation. Okay? If you have a pure generalization style, we can see that you can later on also combine these views. But if you say I have a generalization style, the only thing that you can see here in this view is the modules and one type of relation, which is the inheritance relation. Why should we use this? So everything, every view, every style has some purpose. Okay. Can be used to support object-oriented designs. If your implementation, if your system is an object-oriented, is based on object-oriented principles, so you are using object-oriented design, then this generalization style can support this. Extension and evolution can show, like we have seen here, different type of extensions plus the generalizations. Local change or variations. So one of the key issues is that architecture should be stable. Okay? Stable means that you should have some common parts, that's necessary. But also you need some variations. By using the generalization view, you can, so generalization, you can define commonalities at higher level by defining the subclasses, submodules. You can show what the variations are for each architectural component. Reuse. By defining abstract modules, you can create opportunity for reuse. Okay. This one is larger, so the layer style, that's the fourth style. The element here is layers. Okay. The relations are allowed to use. Relation is again a specialization of depends on. This is an example of a layers view, and the modules here are layers. If layer A, what's the topology constraint? If layer A is above layer B, then layer B cannot be above layer A. Every piece of software is allocated to exactly one layer. What's a layer? This is a kind of layer. It's a layer. It's a collection of software units, such as programs or modules, that may be invoked or accessed. A layer has also an interface by which their surfaces of the layer can be accessed. Okay? Two issues. So a layer by itself includes some modules, implementation units, but the access to these units is provided by some interface. Properties of layering. So every layer, you don't layer just in an ad hoc way, but every layer actually groups modules which relate to the similar concern. We say a layer should be cohesive. It provides a cohesive set of services. The modules are semantically related. They apply to the same kind of concern. Layers are not a function of just who uses what. Okay, that's not the criteria here. but are a result of conscious design decision. What's the consciousness here? By actually grouping these modules which relate to the same kind of concern. Concern is, for example, user interface. All the modules which relate to user interface you put in the same layer. In general, P1 and P2 should be in the same layer if they are likely to be ported to a new application together, if they relate to the same concern. Interface layer provides a set of public interface that might be invoked. In case where the layer is widely used across many kinds of systems and organizations, typically such kind of interface can evolve into a standard interfaces. Okay. Layers actually completely partition the software, and each partition constitutes a virtual machine, kind of virtual machine with a public interface that provides a cohesive set of services. Cohesiveness here means that they relate to the same concern. Because they relate to the same concern, they are cohesive. Okay. Is this sufficient? So imagine we have a system. We just partition the system into layers. Typically, we could then have such kind of alternatives. So why are the below representations not layers? That could be the question. So the issue here is, we will have to break in 5 minutes. The issue here is that besides of the partitioning, so you have a system, you look at specific concerns, you partition the system into layers. One of the second important criteria is that the layers should interact with each other according to a strict ordering relation. The relation is as such: if A, B, these are the layers, is in this relation, we say layer B is beneath layer A, and that means the implementation of layer A is allowed to use any of the public facilities of the virtual machine provided by layer B. So the allowed to use, so layered view consists of partitions the system into several layers, plus it adds some interaction relation. What's the relation? So it's the allowed to use, and typically these layers are stacked. Say layer B is beneath layer A if A uses the services of B. But the reverse is not allowed. Systems with upward usages are not strictly according to the definition layered. Okay? Which means that A is allowed to use B, but the reverse is not possible. What does it mean? B should not know about the details of A. And A can only access B through its interface. Okay? A is allowed to use B. So why is that? Why would we put this constraint here? Why is it not allowed in the layered system that B uses A?
Consider a system which have a user interface, and user interface will be implemented by a C programming language. You cannot you should design a base for higher levels, and this base will be sufficient for A to and A doesn't need to know what is B, because it is a very low level for A.
It is low level, and what would happen if B would know A? If he would call specific functions of the user interface layer.
It cannot be, if B knows A, it would not be, B would not be a low level for according to A.
Okay, but you would also introduce additional couplings, right? It's not the only issue that it should be lower level. Indeed, the lower the layer, the lower the level actually, the abstraction level. But if you would allow users relation to the above layers, we introduce couplings, then we can not easily substitute this layer. That's actually the key issue. Then we cannot just port to another layer. We cannot just put another implementation. It's not possible, because we could have lots of couplings to the higher level layers. So typically the layers below should not be aware of the layers above. Okay? And if they are not aware, you can easily put different implementations in these layers. The only constraint is that you should have the same interface. Before we break, why is the following not a layered system? First constraint, we partition the system into layers. We have it here, A, B, C. That's nice. Typically, we could also say they adhere to the same kind of concern, so we made a deliberate, explicit, nice design decision. And then we define the relations, the allowed to use relations, which is depicted like this. Why is this not a layered system? Even though we have 3 layers here. Why is it not a layered system? Why is it not?
C knows B, B knows A.
Sorry?
C knows B, B knows A.
One violation, C is allowed to use A, but we said lower level layers are not allowed to use higher level layers. You break the constraint, the rule. C is allowed to use B. It's not allowed. B is allowed to use A. All these upwards allowed to use relations are in the strict definition not allowed. In the strict definition, then this is not a layer, basically because of these layers systems. A is allowed to use B, B is allowed to use C. We will see there are some alternatives where they allow that the higher level layers do not only use the next lower level layers, but also a further. Okay? But basically, this violates the rule. Okay. Questions? Okay, after break, we continue with this layered views and module view type. Okay, break.